Hi, and welcome to 10.5b Electric Fields 2. In Electric Fields 1, we kind of calculated the field strength at different positions. And in this homework assignment, we're going to kind of visualize what the field looks like around different charges. And there's a bunch of multiple choice questions here. A lot of them are kind of like logic puzzles, and you have to kind of try to figure it out. So it's kind of interesting there. And then we'll have three questions where we have to draw the field lines. I'm going to go over a couple of the rules for drawing fields, and then if you listen to these, my explanations of the questions will make some more sense. The bottom line, though, is that it's a common misconception that the field only exists on the line. And the field, there's like no field strength in between the lines. That's a misconception. So a lot of people think that, oh, it must be a stronger field right along this line and there's like nothing over here. That's not true. The field lines are basically just a model to represent, it's a way to represent a three-dimensional field on a two-dimensional space. So this field is like, it's not only on the lines, it's spread throughout this entire region. But it is stronger in different areas than in others. So here are the rules. Rule number one is very important. We use a positive test charge to show where the lines point. It's kind of a convention, all right? So lines show where a positive test charge travels. So for example, if you have this positive charge, a source charge that's positive, this thing is creating a field around it. And that electric field I represented in the previous video by kind of like using a highlighter. And you could kind of think of this field as it's three-dimensional, so it's more of a sphere than a circle, right? So the field gets stronger the closer you get. And in a perfect world, I could kind of shade it in better so that there's more of a transition between these. There's no like solid line here. It's hard to draw a three-dimensional field that gets stronger the closer you get to the object. So instead what they do is they made this convention where they use lines that look like vectors, right? Because the electric field itself is a vector. So instead, let's do that. So we draw these lines coming out of the positive charge. But now you have a choice. What direction do you want to make the arrows going? Are they going out of the positive charge or are they going into it? Well, if you put a positive test charge here, the positive repels the positive. So all of these field lines are showing that, yeah, at this position here, if you put a positive test charge, it's going to go away. And the drawback to this, I mentioned it earlier, is that it kind of looks like there's no field at the region between the lines because there's a solid line here. Does that mean there's only electric field right there? And that's not true. That's why I liked to use that highlighter thing, because that's showing that it's the field is throughout the whole region. So that's kind of like the major drawback to the field lines. But as soon as you understand that misconception, then they're actually pretty good. The other thing that we talk about with this is, yeah, if you put a positive test charge here, it's going to go in the direction of the field because by convention, we drew the field where a positive test charge would go. But if you put like an electron in here, the electron is going to be attracted to that positive source charge and it goes against the direction of the field. And that's just because electrostatics is kind of interesting in that you could have a repulsive force or an attractive force. Unlike gravity, if you had like planet Earth here, all right, it's always going to be attractive. So you have Earth, that's the field lines for Earth. And if you have a mass here, it's going to be attracted to Earth. So these are both examples of non-contact forces. We started the year by talking about gravity. And we didn't really talk about the field lines as much with gravity because, honestly, they're not as interesting. It's only an attractive force. But with electrostatics, the field could look different depending on if this is a negative charge. Now we draw the field lines going the other way because a positive charge would be attracted and a negative charge would be repelled by that. Or what if it's like two charges? Now this field looks kind of interesting if we have like the two charges here and they're interacting with each other. The proton or the positive charge is going to kind of go like this and it curves around. Now we have this interesting looking field that looks like this. There's a better diagram of it on number 1. So let's get there quickly. We just have to kind of write out some more rules for us to follow here. So these two diagrams show the next couple rules. You always want to draw your lines going out of positive and into negative charges. Also, the good thing about using these lines like this is that it shows the strength of the field. So instead of like a light, like in my previous example, or the color of the highlighter, the darker the color, the stronger the field, what this is showing is the closer the lines are to each other, the closer the field. So as you get closer to the sphere, the lines are really close together. The further out you go, the lines are further apart. So that's the second rule, is that the closer the lines, the stronger the field. And because of that, rule number 3 comes about. We can't have the lines cross each other, because if we're saying that the closer the lines are to each other, the stronger the field is going to be. So here, see, I'm drawing it wrong already. Lines can't cross. The closer they are, the stronger the field. So at this position, it's a lot stronger than over here. Well, what if I drew them so close together that they were on top of each other? Maybe it's like this. At this point, they're so close together, they're on top of each other. It's almost like saying there's an infinitely strong field, which you wouldn't have. So you don't want to have the lines cross each other. They can't cross. And the fourth thing to keep in mind is just that the lines are a two-dimensional model of a three-dimensional field. And you want to keep that in mind, again, because it's not showing that the field only exists where there's a line, and that where there is no line, no field exists there. That's not what it's showing. It's a way to represent. There is limitations to this two-dimensional model, but it's a way to represent a three-dimensional field. Obviously, if you could take a picture of it or something like that, then it would be better, but you can't really take a picture of it. You kind of have to visualize in your mind what it looks like, and the lines are here, and they're drawn according to these rules to help you visualize what the field looks like. All right, let's do some problems. So now that we're familiar with the rules and how these lines are drawn, we could do these multiple choice problems that are kind of like logic puzzles here. So it says the diagram below represents the electric field surrounding two charged spheres, A and B. Then it says, what is the sign of the charge of each sphere? So you have to look at the direction of the arrows. The direction of the arrows definitely tells you at least one thing, whether the thing is positive or negative. So they're coming out of B. So if you put a positive test charge here, it's going to go, so this is positive, it's going to go in this direction, away from it. And what does that tell you about B? It's going to be repelled, right? So B is a positive charge. And they're going into A. They're all going into A. So now we have a positive charge here, and it's being attracted to A. So what does that tell you about A? A must be a negative charge. Okay, so sphere A, let's see. It's choice B. Sphere A is negative and sphere B is positive. So for C and D, it's saying both spheres have the same charge. I knew right away it's not C or D because the way these field lines are drawn, it's showing an attractive charge, an attractive field. Okay, number 2. Two small metallic spheres, A and B, are separated by a distance as shown. The charge on sphere B is 1 microcoulomb. Point P is located near the spheres. Which arrow best represents the direction of the resultant electric field at point P due to the charges on sphere A and B? All right, so A is positive and B is positive. So this one is going to exert a force on point P. If you put a positive test charge there, that is repulsive. So you could draw the vector like this. And then sphere B also has an identical force pushing the other way. It's going like that. So that's what they're saying, the resultant electric field. Now we have to find the resultant of those two vectors. And how do you add vectors? Head to tail. So you have to take this guy, you move it over here, and now you have them head to tail like that. Let me see if I drew these identical. Okay, that's pretty good. And now the resultant vector is from start to finish. So you draw like this. So when you add those two vectors together, the field from this one plus the field from this one, at that point, you get a resultant vector that points upward. And you could kind of visualize, instead, if you didn't want to do like vector addition and do it like that, what you could do is, in your mind's eye, place a positive test charge here. And then try to visualize, okay, this one's pushing me this way, this one's pushing me this way because they're both positive. What direction am I going to go? Well, since they're both pushing me in opposite directions, but they're both pushing me upward, it's going to push me upward there. So that's the best choice from the choices there. All right, number 3, it's kind of referencing what I mentioned in number 1, where I said, oh, this is an attractive field. Well, what does a repulsive field look like? So they kind of show what the field lines look like here. It says, which diagram represents the electric field lines between two small electrically charged spheres? So you just have to look through these carefully and see if any of them break the rules. All three of these are going to break the rules, and one of them is going to be good. So let's look at A. A shows the lines coming out of a positive charge. So far, so good. But now they're showing them going into a positive charge. And a positive test charge would not be attracted to this guy. It would be repelled away. So this is not going to work for us. It's not A. For B, we have the lines coming out of a positive charge and out of a positive charge. That's looking pretty good. This is actually the field lines for a repulsive field, where in the middle, the fields exactly cancel each other out. So if you did that vector addition thing again, where you have the lines there and then you add them head to tail, the fields exactly cancel each other out right in that center point, provided that they're equal charges on both sides. But that's not the question's asking. It's just saying, is the direction of the field correct? Okay, let's double check and see what C is doing. So C is showing that if you put a positive thing right here, it's going to be repelled away from this negative charge. I don't think so. It better be attracted to that. So the field lines are actually in the opposite direction. Same thing. If you have a positive thing here, it's not going to be attracted to that positive charge. So this is no good. These arrows should be flipped the other way. And for D, it's showing, okay, so this side looks identical over here. So that was good before. We like that. We like that. The positive is going out of the positive. So that's good. But how about on this side? If you put a positive test charge here, it would be attracted to this negative charge. And you would get field lines that look like this, but obviously flipped in the opposite direction, like we said. So that's no good either. All right, so it's choice B for that one. Number 4 says the point P is near a negatively charged sphere. Which vector best represents the direction of the electric field? Electric field lines always go into the negative, so it should be choice A. Positive test charge here would be attracted to that. 5 is tricky, so this is like a logic one. An electron, people, this is negative. A negative electron is placed between oppositely charged parallel plates and moves towards plate A, as represented in the diagram below. They're oppositely charged, and it moves towards plate A. If a negative thing is attracted to something else, this is probably going to be positive. It is. Not probably, but it is. All right, it's attracted to A, and since it's oppositely charged, we know this must be negative, which also makes sense because the negative is going to repel that negative electron away. Okay, so far so good. Now it says, what is the direction of the electric field between the plates? By convention, the electric field is drawn where a positive test charge would go. So if you put a positive test charge here, not this negative electron, but a positive test charge, then you would be repelled away from this and attracted to this. So the field itself is actually going down the way it's drawn here into B, which is opposite what the negative electron is feeling, but we would expect that because the field lines by convention are drawn where a positive test charge would go. So that's the explanation for that. They go towards plate B. And when it's saying into the page or out of the page, they're using the third dimension here, right? So you could either go up and down, left and right, or you could go into the page or out of the page. Sorry, into the page or out of the page. We'll talk about those X's and O's when we do magnetism. So these field lines get a little bit trickier when we talk about magnetism too. Number 6. The diagram below represents a positively charged particle. Okay, so this is positive as shown. And it's about to enter the electric field between two oppositely charged parallel plates. The electric field will deflect the particle. This guy, it's a positive test charge. The field looks like this. So as this goes in, it's going to curve downward like that. It gets repelled by the positive plate and attracted to the negative plate. So it's going to go down towards the bottom of the page like that. Number 7 says the magnitude of force exerted on the charges by the electric field between the plates is, it's going to be the same for A, B, and C. Here's why. All right. A is super close compared to B and C. It is closer to the positive plate. So as you move down, it's a weaker and weaker repulsion force because this is so far away now. It's not going to repel it as much as C as it does in A. So we got that idea. Now for the negatively charged plate. So it's also being attracted to this. C is really close to that negatively charged plate. So you have more attraction here, moderately attracted there, and it's not that attracted here. And the idea is with these parallel plates is that when you do the vector addition, like this, of the attractive force and the repulsive force together, let's see how well I drew this. Decent, maybe? I don't know. Not really. They should get the same size. So I'm looking for equally sized vectors when you add them all together. And let's see how we did. That's pretty much the same size, but I kind of screwed up with this. Right, so this should be the same size. Oops. All right, I think you guys will forgive me, though. Hopefully this makes sense. It's a combination of the repulsive force and the attractive force. And when you add them the two together, it's kind of like a balancing act as you go through the field from here to here. And the sum of those vectors remains the same. All right, for A, B, and C. Okay, number 8 says, the diagram below shows the arrangement of 3 charged hollow metal spheres A, B, and C. The arrows indicate the direction of the electric forces acting between the spheres. At least 2 of the spheres are positively charged. Interesting. So at least 2, maybe all 3 are positively charged. Which sphere, if any, could be negatively charged? This is another good logic one. See if you could try to figure it out definitely before you listen to the explanation here. So let's just take it one interaction at a time. Let's look at the forces between A and B. So we're looking at this one and this one. B is attracted to A. I know that because it's being pulled this way. So B is attracted to A. A is being pulled towards B, as shown. So this is going to be attractive. Now let's look at A and C. A and C, only those 2 forces, right? So let me draw it like this, like I did before. All right, A is being pulled towards C. C is being pulled towards A. So it's another attractive interaction. So right off the bat, because there are these attractive interactions, even if there was just one attractive one, we know there must be some opposite charges. And we know that it's not, yeah, they're saying at least 2, And it's only two because at least one of them has to be negative. There needs to be opposite charges in order for this attractive force to be happening. All right, let's look at B and C. B is being pushed away from C, and C is being pushed away from B. So there's a repulsive force there. And if we know that two of them have to be positive, and we know that there is a repulsive interaction here, then we know that B must be positive, and C must also be positive. Now let's see, what does that mean for A? Well, there's an attractive force here between these two, so A must be negative. And let's double check. A and C, attractive force, positive and negative, that makes sense too. So as you can see, it's kind of like a logic puzzle. You have to make the pieces fit. So it says which sphere could be negatively charged? That's going to be sphere A. Very good. All right, number 9, sketch the electric field lines in the following situations. Follow the rules for sketching lines. So we're going out of positive and into negative. If I put a positive test charge here, the positive test charge would be going in this direction here. So we don't actually draw the positive charge. We just draw the field line going like this. And in between these two, how do I know it's curved, right? So if I put a positive charge here, this guy, the positive source is going to push this away. But it doesn't just go off into infinity, because you also have this negative source charge pulling it back in. So instead of drawing like, and then we kind of like add the vector sum for all those vectors, and we just draw a line like this. Okay, and same on the other side. And it's the strongest in between the charges here. And as you go further out, the lines get further apart because the field is weaker. Kind of like this. Pretty poorly drawn, but you get the idea. Okay. As long as they're going out of positive and into negative, and you have this bit in the center, and if you do your best effort, oh man, if you do your best effort on the outside and you're trying to make everything symmetrical, your lines don't cross, you get an A for effort. And that's kind of what the field looks like. Okay, for B, it's showing a positive and a positive, so it's not going to be attractive, it's going to repel away. So if I put a positive test charge over here, not only is it going to be pushed away this way, this guy is also pushing away. And when you combine all these vectors together, you get something curvy like that. So let's draw these field lines here. This one goes like that. That one goes like that. I kind of got overzealous. They're pretty close together, and you don't want the field lines to cross. That's important. You want to try to be as symmetrical as possible with this. And something like that would suffice. They're all pretty curvy, except for that one. Okay, so that's the idea there. Again, an A for effort. Now it says draw the electric field lines in between the two charged metal plates. So again, you want to visualize, if I put a positive test charge here, where's that thing going to go? So you're either first looking at this plate and determining, or you could first look at that plate, you get to the same answer. Let's look at the negatively charged plate first. I have a positive and a negative. It's going to be attracted to it and go up. Let's verify with this positive plate here, it's going to repel the positive charge. And yeah, all the field lines are going to be going up in this situation. So let's draw them. And as you draw them, you want to try to draw them as equally spaced and symmetrical as possible. You could either draw them all really close together or really far apart. Technically, as long as they're equally spaced and going in the same direction, you're getting the idea. All right, that's about it. Have a good day.